Most people imagine Tyrannosaurs battling giant hornheads, chasing down chunky hadrosaurs, or ambushing the quick-footed ostrich dinosaurs. But what if the real horror was much closer to home? 4 separate studies, 4 different sets of fossils, drawer monsters in Montana, a skull in Alberta, a mangled metatarsal in Wyoming, and bite-marked remains in New Mexico. Each line of evidence points to the same conclusion. Tyrannosaurs did occasionally munch on other tyrannosaurs. Were these brutal attacks during life, or signs of scavenging the dead? Either way, it points to something often left out of the T-Rex story: cannibalism. And when all the pieces are put together, the picture is hard to ignore. Imagine walking through a museum gallery, staring at the massive skeleton of Tyrannosaurus rex and noticing not just cracks or chips in the bone, but deep, U-shaped grooves carved straight into the fossil. Not subtle scratches either. These marks cut across the bone surface in arcs that match exactly what you'd expect if enormous serrated teeth clamped down with crushing force. That mental picture is already strange enough, and it gets stranger once you realize the only jaws big enough to make those gouges belonged to another T-Rex. Looking at these fossils today, it almost feels like walking into the aftermath of a prehistoric crime scene, where the victim and the suspect are the same species. This puzzle first really came together in 2010 when paleontologists Nick Longrich, Jack Horner, Gregory Erickson, and Phil Curry examined museum collections looking for overlooked bite marks on tyrannosaur fossils. Museums had stored these bones for decades, sometimes on public display, other times in drawers and storage rooms. No one had paid too much attention to these scratches or punctures before, because researchers often focused more on pulling whole skeletons together for study. But Longrich and team deliberately searched for feeding evidence, checking for marks where predators had raked across bone while stripping flesh. Their survey turned up 4 different T-Rex specimens: UCMP 137538, Moore MOR 1126, or C.rex, MOR 920, and MOR 1602, each with unmistakable damage, bites that could not have reasonably come from any other predator but a tyrannosaur. They published their work in PLOS ONE in 2010. UCMP 137538 is a toe bone. MOR 1126 is a partial skeleton, as is MOR 920, and MOR 1602 is a foot bone. Along with the Tyrannosaur's bones with bite marks attributable to other tyrannosaurs, the researchers also scoured over a bunch of bones from other dinosaurs that also had tyrannosaur bite marks on them to compare and contrast, such as ceratopsians, edmontosaurs, generic hadrosaurs, and bipedal ornithopods, like Thescelosaurus. It turned out that limb and foot bones showed the clearest evidence. These weren't the glamorous areas with slabs of muscle like the thigh or torso, which carnivores would normally target first. Instead, the marks appeared on less meaty bones, like the metatarsals and humeri, suggesting whoever made them wasn't hunting for prime cuts, but scraping away whatever was left after death. That detail makes a difference, because it hints the animals were picking apart carcasses, chewing right down to the tougher bits when food was scarce, or maybe when a rival's dead body was the only available meal. In either case, the image is a little chilling. One of the largest predators of all time, gnawing on the foot bones of its own kind. How can paleontologists be sure these weren't made by some other late Cretaceous carnivore? The answer comes from the size, distance, and curvature of the marks. The gouges are simply too wide and too deep for these smaller meat eaters of the same age, such as crocs, dromaeosaurs, or even smaller tyrannosaurs. As far as consensus knows, T-Rex monopolized the top predator role in its ecosystem, which makes the match between tooth marks and jaw size pretty much a perfect fit. The spacing between parallel grooves lines up with the characteristic ridges of a tyrannosaur's serrated teeth. You can even measure them and plug the numbers back into the estimated bite force and tooth size, and everything points towards an adult T-Rex as the biter. Of course, there are always questions. Could the marks have come from some kind of territorial shoving match that left accidental scars? Maybe two tyrannosaurs locked jaws in combat and one left a mark before the other yanked free. The issue with that idea is the location of the marks. Combat wounds tend to appear on the head, face, or flanks, where animals actually bite when fighting. Marks on the foot and limb bones don't really fit with dominance battles. They line up much more neatly with feeding traces. Add to that the fact that there's no sign of healing around these specific scars, meaning the animal was already dead when the bites happened, and the case for feeding over fighting gets stronger. When Longrich and co-authors weighed the alternatives, they came to the most straightforward explanation: cannibalism. Not necessarily organized hunting of living rivals, but the opportunistic tearing apart of corpses whenever the opportunity appeared. It might sound extreme, but in a world where food didn't come packaged or delivered, a carcass represented free calories no matter whose carcass it was. So the evidence showed, for the very first time in the scientific literature, that T-Rex sometimes ate its own kind. This single conclusion changed how paleontologists looked at the king of the dinosaurs. If the tyrant lizard was willing to scavenge or even prey on its relatives, then the drama in those Cretaceous floodplains was more violent and complicated than anyone had envisioned before. Just when the shock of that discovery was setting in, fossils from Canada revealed an even grislier story, one that played out not on the limb bones, but right across the face. What's more brutal than finding bite marks on a dinosaur's arms and legs? Finding them right across the skull, and even worse, realizing the animal actually survived some of those encounters. That's exactly what happened with a specimen of Daspletosaurus, a close relative of T-Rex, found in Alberta by Phil Curry back in 1994 in the lower part of the Dinosaur Park Formation in Dinosaur Provincial Park. Flash forward 20 or so years, and paleontologist Dave Hone and Darren Tank finally get around to publishing this specimen to focus on the skull and the story it told. Their work was published in PeerJ in 2015. The story the skull told wasn't just about combat or feeding, it was both. The bones carried the signatures of life and death struggles etched permanently into their surfaces. The skull in question belonged to a large animal, though it was clearly not fully mature. Specimen TMP 1994.143.0001 is identified as a Daspletosaurus, but which of the three species it belongs to could not be identified due to the specimen's age and preservation. Right away, the researchers could easily tell that it had lived a violent life. When Hone and Tank examined it carefully, they spotted a number of punctures and gouges on the facial bones. The kicker? Some of these injuries showed obvious signs of healing. Tyrannosaur bone reacts to trauma just like ours does. It can remodel and knit itself back together. That means the animal wasn't just struck once and immediately killed. Instead, it took those bites, survived, and carried the scars forward while it continued to live, hunt, and fight. Alongside the healed wounds, there were other marks with no sign of recovery at all. These appeared on the lower jaw region, especially the dentary bones. The pattern resembled gnawing marks, furrows that matched the tooth shape of another tyrannosaur. Because there was no new bone growth triggered around these particular marks, the only logical explanation is that they happened after death. The skull had been scavenged. That means at least one individual had come across the carcass and torn into it, treating what had once been a combat opponent as a meal. That's how paleontologists draw the line between fighting behavior and feeding behavior. If you see healing, the injury happened during life. If there's no healing, it must have been post-mortem. This distinction is what makes the specimen such a powerful case study. It demonstrates two different behaviors recorded in the same fossil: intraspecific combat and later cannibalistic feeding. It's not hard to picture. Imagine this animal when it was alive, stalking prey, already marked by old bite scars across its skull. Every healed puncture says it survived a violent confrontation with its own species. Fast forward to its death, its flesh attracting other carnivores. A rival drew in, tested the body with a few exploratory bites, and then tore through the tissue, leaving tooth scars pressed into the very bones of the jaw. Taken together, the specimen captures a full cycle of interaction: combat in life, consumption in death. That's not something that often preserves in the fossil record, which is why the skull is so important. It also shows that fighting and feeding shouldn't be thought of as totally separate behaviors. Modern carnivores blur those lines all the time. A crocodile biting another crocodile might not kill it, but if it later stumbles across the corpse, it certainly won't ignore the opportunity. Lions claw and bite rivals in territorial disputes, and when one goes down, it can become food. What happened with this tyrannosaur fits comfortably within that broader ecological pattern. They were competitors, but also potential meals, depending on circumstances. It also proves that face biting and cannibalism were going on in this dinosaur group long before Tyrannosaurus existed. This wasn't a one-off oddity reserved for a single unlucky individual in Alberta either. The same pattern of violence and feeding resurfaces further south, where the bones of a much younger T-Rex tell an equally unsettling story. If young adult to adult T-Rex tearing into each other sounds bad enough, the fossil record adds a layer that is somehow worse. Evidence shows that juveniles also wound up as meals for their own. That scenario comes from a discovery in Wyoming's Lance Formation, published in 2018 by Matt McLean, David Nelson, Keith Snyder, Christopher Griffin, Bethania Sevito, Leonard Brand, and Arthur Chadwick in the journal Palaios, in which a single lower leg bone, specimen SWAU HRS 13997, from a young Tyrannosaur, revealed damage so distinctive that the case for cannibalism was most parsimonious. The bone wasn't just pockmarked or scored randomly. It carried one of the clearest trace fossils ever found of a serrated tyrannosaur tooth running directly over its surface. Ichnology, a subdivision of paleontology, is the study and classification of fossilized traces, which usually involves footprints and burrows but can also include bite marks. And this one on the tyrannosaur bone was identified as Nethicnus parallelum, which describes the way serrations on carnivorous teeth carve neatly into bone like a saw blade. Seeing it so cleanly impressed into a tyrannosaur bone made one thing obvious: this wasn't caused by trampling, or by erosion, or even by another predator species. It came squarely from one tyrannosaur biting into another. This is where the study stands apart from earlier cases. Many bite marks on fossil bones look like rough gouges or splintered punctures that could, hypothetically, come from multiple animals of similar size. In this Wyoming example, the serration drag leaves behind an unmistakable profile, almost like a fingerprint. Microscopic ridges from the tooth edge line up exactly with the patterns expected for tyrannosaurs. The authors counted, measured, and compared them with known tyrannosaur teeth from the Lance Formation, and the match held together. That level of detail leaves precious little wiggle room for interpretation. It wasn't some opportunistic crocodile, nor a raptor trying to gnaw something too large for it. The sheer width of the bite and the serration spacing limit the candidate list to adult or subadult T-Rex. What remains harder to pin down is the behavior behind it. Scientists debate whether this specific bite represents predation, an adult actively killing and consuming a juvenile, or scavenging of a carcass that had already died for other reasons. Both possibilities make sense in ecological terms. In many modern ecosystems, large predators kill young rivals simply because they compete for resources, and opportunistic feeding often follows. On the other hand, carcasses rarely go to waste in the wild. In harsh environments with fluctuating food supplies, anything that dies can and will be recycled, including members of one's own species. What tips the scale here is the placement of the mark. The bite occurred on a foot bone, an area not rich in meat. That leans towards scavenging rather than a deliberate kill, although it doesn't rule predation out entirely. If an adult T-Rex killed a juvenile outright, tearing into the fleshy torso would make more sense. Instead, what we have is one tyrannosaur chewing down into the tougher, less rewarding portion of a relative's skeleton. That behavior suggests either desperation for calories or a simple lack of other food sources. Either way, the fossilized tooth scrape captures the end result: one tyrannosaur feeding directly on another. Cannibalism wasn't just a phenomenon of adults fighting each other in territorial battles like we saw in the Albertan fossils. It extended to the youngest animals, leaving open the possibility that age and size didn't guarantee any safety from becoming dinner. And this pattern isn't limited to the north in Canada, wild buttes of Montana, or even the grasslands of Wyoming. Further to the southwest, fossil evidence from New Mexico carries its own story of earlier Tyrannosaur species scarring and consuming each other in ways that echo yet again the same unsettling theme. Picture a late Cretaceous floodplain in what is now northwestern New Mexico. Herds of horned dinosaurs and hadrosaurs trudge through the mud, while scattered groups of tyrannosaurs pace the same ground. The tyrants here weren't just worrying about chasing down prey, they were also dealing with each other. That image is what paleontologists Sebastian Dahlmann and Spencer Lucas brought into focus in a 2021 study of fossils from the San Juan Basin in the New Mexico Museum of Natural History and Science Bulletin. The bones they described carried bite marks that leave little doubt that in this part of the world, tyrannosaurs weren't just the top predators. They were also each other's enemies, and from time to time, someone else's next meal. The evidence came from 3 different bones, each telling a different part of the story. The first specimen, KU-VP96888, was a partial dentary, or part of the lower jaw, from the late Campanian-aged Nenonezed member of the Fruitland Formation. When the researchers examined it, they noticed impressions they identified as pre-mortem injuries. In plain terms, the animal took a bite across its face during life and survived long enough for its bone to heal. The bite had gouged into the surface, yet the bone responded by depositing new tissue to close the wound. That's how paleontologists know it wasn't post-mortem damage. This was an intraspecific attack, one tyrannosaur shoving its teeth into the face of another. A second fossil from the late Maastrichtian-aged Nashoibito member of the Ojo Alamo Formation told a different story. This one, NMMNH-P40953, was a caudal vertebra, part of the tail. Here, the marks were unambiguous feeding traces. No healing at all, only clean impressions where teeth had forced into the bone's surface. They were the kind of punctures that form when large serrated teeth pierce through soft tissue and scrape down against solid bone. Because of their size, orientation, and spacing, these bite traces were attributed to another tyrannosaur. The most telling specimen was a femur, specimen NMMNH P25083, from the late Campanian-aged Denazin member of the Kirtland Formation. Not only did it show parallel drag marks, but also crumpled edges where the bite pressure squeezed bone until it fractured. This kind of damage can be matched to specific feeding motions. Again, there was no sign of bone healing. These marks represented what happened after death, while another tyrannosaur was feeding in earnest. That created a kind of layered picture: jaw trauma during life revealing combat with rivals, and skeletal scarring after death revealing consumption by kin. Dahlmann and Lucas noted the main categories of tooth damage the fossils carried. There were punctures, which show the teeth entering straight into bone surfaces. There were scoring marks, faint but repeatable parallel traces from the serrations of tooth edges being pulled across bone. And there were areas they described as collapses, where bite pressure caved in thin bone. Each of these tells something about feeding style. Punctures lined up with forceful bites. Drag marks align with the motion of cutting away flesh. Collapses follow when one animal chews until weaker bones buckle. Having several types of marks across different skeletal parts makes the interpretation much stronger, and it also mirrors what has been seen in fossils from Canada, Wyoming, and Montana. The bigger takeaway wasn't just that individual animals showed evidence of fights or corpse reuse, it was that in this region, across different specimens, the pattern repeated itself. Some tyrannosaurs bit each other on the face and went on living. Others, dead or dying, became resources for survivors. These weren't isolated freak incidents, they were part of an ecological system where the line between competition and consumption blurred. Intraspecific aggression and cannibalism weren't separate boxes, they were behaviors that overlapped, depending on whether the victim survived the encounter or not. So, in the San Juan Basin, the image is of tyrannosaurs coexisting in stressed environments where both confrontation and cannibalism were routine. Jawbones, tails, and limb bones all document the cycle. A face bite leaves a healed scar. A tailbone carries the scars of feeding. A femur bears the crushing mark of jaws stripping muscle from its surface. Together, they strengthen the conclusion that tyrannosaurs routinely turned on their own. But was that habit something unique to tyrannosaurs themselves, or was it actually just part of a much older and wider pattern among carnivorous dinosaurs and even modern predators? If tyrannosaurs weren't the only dinosaurs to eat their own, the obvious next question is who else did? Paleontologists have been asking the same thing for well over a half century, and the answers show up in different corners of the fossil record. One of the most famous early examples is from the late Triassic-aged Ghost Ranch site in New Mexico, where hundreds of skeletons of the small predator Coelophysis were preserved together in a massive bone bed. When these fossils were first studied back in the early 20th century, some researchers thought they saw little skeletons inside the rib cages of larger ones. The conclusion they drew was that Coelophysis sometimes ate its own young. That interpretation held for many years, and the image of Coelophysis mothers crunching down on their babies made its way into books and documentaries. But later studies, using CT scans and careful anatomical comparisons, found that these supposed juveniles inside weren't young Coelophysis at all. Instead, they were pieces of other animals, like crocodile-line archosaurs. That reinterpretation showed how easy it is to mistake the jumbled bones inside stomach cavities. So, for Coelophysis, the cannibalism case is weak, and most paleontologists today are skeptical of it. On the opposite end of certainty is Majungasaurus, a large abelosaurid from late Cretaceous Madagascar. Here, the evidence stacks up much more firmly. Dozens of Majungasaurus bones, limbs, ribs, and even vertebrae have been recovered from different sites, with tooth gouges carved directly into them. The spacing and size of these marks line up with Majungasaurus teeth, and no other predator large enough was roaming the ecosystem. In fact, statistically, Majungasaurus bones are just as likely to show bite marks from Majungasaurus as herbivore bones are. That pattern suggests it wasn't a rare freak event, but something that repeated itself across the landscape. The image is not of anomalous cannibalism, but of a normal feeding behavior when carcasses were available. Majungasaurus probably switched between scavenging herbivores and scavenging dead abelisaurs, and maybe even predation when rivals were injured. It's one of the clearest windows into cannibalism among dinosaurs that scientists have ever had. When you set these examples alongside the Tyrannosaur fossils, you start to see an even larger pattern. Across different continents and time periods, big predatory dinosaurs sometimes treated their own kind as food. In Tyrannosaurs, the evidence often comes from combat and scavenging scars, like healed face bites and unhealed gnaw marks. In Majungasaurus, it's abundant tooth scores. And even if Coelophysis is off the list, the fact that the bait lasted so long says something about how tangled bone beds can mimic cannibalism. You can put this into perspective by thinking about how modern animals act. Lions sometimes kill rival lions, and though they don't always eat them, scavenging does happen. Hyenas go further and sometimes will consume members of their own clan if resources wear thin. Crocodiles both fight and feed on one another, driven by territorial overlap. Bears are notorious for cannibalizing cubs. In most of these cases, the behavior isn't pathological or unique to individuals, it's ecological. If food is scarce and you stumble across a body, whether it's kin or not, you take the calories. That's probably what we're seeing in the fossil record for theropods, and it's almost certainly underreported because the evidence is so fragile. Paleontologists work with fossils that have been buried for millions of years. Tooth marks weather away, scavenging often leaves only subtle traces, and skeletons rarely preserve with enough surface detail to catch them. Healed wounds require skulls and jaws intact enough to see remodeling bone. When we do get these rare fossils where feeding traces are obvious, it's not unreasonable to assume they stand for a much bigger background pattern, hidden by preservation bias. So when paleontologists talk about T.rex eating T.rex, the important thing is not whether it was a grotesque outlier. It's that the behavior fits into a broader story of carnivores across deep time. From Madagascar to North America, from abelisaurs to tyrannosaurs, these same ecological pressures show up. Large predators competed with each other, they sometimes killed each other, and when death left a heavy carcass behind, another member of its species often became the one to chew through it. Cannibalism for T.rex wasn't an exception or some bizarre malfunction, it was something that came with being a massive predator in a crowded ecosystem. When food ran thin, a dead tyrannosaur was still energy, and survival came first. So maybe instead of seeing it as terrifying excess, we should see it as survival discipline, a ruthless but practical adaptation. If the king of the dinosaurs fed on its own, what other hidden habits are locked away in bones we haven't read closely enough yet? The fossil record keeps rewriting itself, and there's no telling what's still waiting to surface. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, like this video, drop a comment in the comment section below, and hit the bell icon to stay in the know with everything Edge. Thanks for watching.